Well, hello. This is the second video on kinetic molecular theory, and we're based in Young and Freedman's University Physics. The chapter we're in is chapter 18, the thermal properties of matter, or the heat properties of matter. And as I said, this is the second video covering the kinetic molecular model. This is a very thick section having to do with the pressure associated with individual molecules, the kinetic energy associated with individual molecules, the molecular speeds of individual molecules, and so forth. It's so thick that at present I've divided it up into three sections, and this is the second. The first video was on collisions and gas pressure. So we ended that video with an equation that expressed the pressure or the force per area of molecules upon the walls of a container. We express that in terms of the total number of molecules, the mass of each individual molecule, and the velocity, the x component of the velocity squared of those molecules per volume. And that's how we ended our previous section. Well, that took 10 minutes to do that, and so I'm hoping in about 10 minutes to explore the second subsection of this section, which is on pressure and molecular kinetic energy. So we're going to talk about the kinetic energies of these molecules, gas molecules. So how do we figure out the total kinetic energy? And I will say we're talking here about translational kinetic energy. That is basically X, Y, and Z kinds of kinetic energy. There are, especially with bigger molecules, rotational kinetic energies, vibrational kinetic energies, but we're going to suspend talk about them until later in the chapter. For now, we want to talk about translational XYZ kinds of motion of the molecules. Now, the previous section, we focused on the X component of the velocity as it was running into the rigid walls of a container. But if we wanted to know the total kind of velocity of the average velocity of all of these molecules going in all different directions, we would do a little Pythagorean voodoo, where the v squared average, the average velocity squared, equals the x components of all these squared plus the y components of all these squared plus the z components of all these squared. Now, the previous section treated these velocities as if they're all the same. In reality, they're not. So we're really talking about the total average. However, even though the total average, even though the individual ones may be going at different speeds, it really doesn't matter whether we're talking about the x or y or z direction when it comes to all of these, because really, they're moving fairly freely. And so these three components, for all intents and purposes, are going to each be the same. So you could say that, say, the Vx component squared is going to be a third of the total velocity. If this is a third, and this is a third, and this is a third, then this is going to be a third, of this. We can say that. Okay, we're moving toward the total kinetic energy as relates to the translational component. So how are we going to come up with that? Well, in the previous video, this is the formula. I just spoke it. From the previous section, this is where we ended up. That the pressure in a volume is equal to the total number of molecules times the mass of those molecules times that, x component squared of the velocity. Okay, that's what we ended up in the previous section with, previous video. So if we multiply the V out, multiply V by both sides, we end up with PV equals this. And we just said that the X, remember, we just said that the X squared equals 1/3 of the total average. So we can substitute that in, 1/3 of the total average squared, and voila! We now have an expression that says that pressure times volume, PV, equals 1/3 times the total number of molecules in that space times the mass of each individual molecules times the square of the average velocity of all of the molecules going in the x, y, and z direction. Okay, now we're getting somewhere. because we also know that okay, so here's what we're going to do next. We're going to do a little algebra voodoo. We're going to take 1/3 and we're going to pull 1/3 apart into 2/3 times 1/2, right? Because the 2's cancel out and you're left with 1/3. So I can pull the 1/3 apart into 2/3 times 1/2. Why would you do this, you crazy man? Well, because once we do that, we have the 2/3 n part out here, and I'm left with 1/2 mv squared. Well, does 1/2 mv squared sound familiar? Well, of course it does. That's the formula for kinetic energy. Kinetic energy equals 1/2 mv squared. And so basically I have PV equals 2/3 n times the translational energy. And so 2/3, there's the 2/3. There's the kinetic for each individual molecule, which times the total number of molecules gives me the total kinetic translational energy. Okay, great. Okay, that's where that came from. This is the kinetic energy of an individual molecule, and this is all the number of molecules, and so there you have it. PV equals 2/3 times the total translational kinetic energy. Okay, so let's see if we can find the kinetic energy for a single molecule, because remember, this is the total translational kinetic energy of all of the molecules, okay? So what am I going to do? Well, I remember that PV equals nRT, and I now know that PV equals 2/3 times the total kinetic translational energy, okay? But, so now I'm going to do a little more voodoo. I'm going to take the 2/3, and I'm going to transfer it to this side by multiplying both sides by 3/2, right? 3/2, the 3's cancel out, 2's cancel out, and so that goes away. It's gone. But then I have 3/2 on this side, so total translational kinetic energy equals 3/2 nRT. Okay, so now if I divide by the total number of molecules, so I'm going to divide this side by the total number of molecules. I'm going to divide this by the total number of molecules. See, 3/2 nRT, 3/2 nRT, and then I've divided both sides by n. I'm allowed that in algebra. As long as I divide both sides by the same thing, it works. And now I'm left with 3/2. Now, there's the RT. How did I get the NA? Well, the number of molecules, the number, hold on a second. So small n is the number of moles, right? Number of moles. And so the number of moles equals the total number of molecules divided by Avogadro's numbers, 6 times 10 to the 23rd power. Okay, so what I'm going to do, what I've done here, and I didn't do it, Young and Freedman did it, is I substituted in n over Na here, n over Na. So I've got the 3RT is still there. N over Na, there's the Na ended up, what happened to the big N? The big N canceled out. This times this canceled out. And so I was left with R over Na. Okay, so here I've got another formula. Why did they do this? So this is the energy, another way of saying the kinetic energy of a single molecule. Now, here's where we get Boltzmann's constant. Boltzmann was a very intelligent man in the late 1800s who, I believe he committed suicide, which is very unfortunate. But anyway, sometimes very smart people can be depressed, which is really too bad. But anyway, R over Na is sometimes called a Boltzmann constant. Remember, this is the gas constant in relation to moles. R is 8.3 blah 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 joules per mole Kelvin, and then Avogadro's number is 6 times 10 to the 23rd molecules per mole. And so we come up with another constant out of these constants, and its symbol is a small k, and it's basically 1.38 times 10 to the negative 23rd joules per molecule Kelvin. Okay, and you see that this is basically once the smoke clears from all this crashing together and canceling out, it ends up joules per molecule Kelvin. Okay, so we can now reformulate. So remember, the total translational kinetic energy divided by the number of molecules, which just gives me the kinetic energy per molecule, equals this, which we figured out on the last slide, and we now can define this as K. There you have it. And that equals the kinetic energy of each individual molecule. Phew. Okay. Well, of course, wherever Young and Freedman have a number out to the side, that's a kind of formula that you may want to use in a particular situation where you're given a problem with, you're given certain variables, you don't have other variables, and so you take whichever equation has the variables that you have, and you solve for it. So our last thing is this is the amount of kinetic energy per molecule, okay? All of this, different formulations of kinetic energy per molecule. What about kinetic energy per mole? Well, again, this is the kinetic energy per molecule. If we multiply it by Avogadro's number, which tells us the number of molecules per mole, 6 times 10 to the 23rd power, this is going to equal 3RT, right? 3RT, because when you multiply 3/2 R, over Na times T times Na, the Na cancels out, and you're just left with 3/2 RT, which, by the way, equals the molar mass. Let me see if I have that. The molar mass is this is the number of grams per mole, and the number of grams per mole equals the mass of each individual molecule times Avogadro's number. Anyway, it all works. So these are all different ways of saying the same thing. So finally, we can reformulate the ideal gas equation, PV equals nRT. So remember, the number of moles equals the total number of molecules divided by Avogadro's number. And if we take the Boltzmann constant, the Boltzmann constant equals R over Na. So R equals Na over K. So we can substitute this in for N and this in for R, and we're left with PV equals NKT. Because when we multiply these two together, the NAs cancel out, and we're left with NK. And so NK substitutes for NR. So this is another way of expressing the ideal gas constant. The Boltzmann constant tends to be a constant that relates to per molecule, whereas the N constant relates more to per mole. And so depending on which kind of situation you're in, one or another of these forms might seem more helpful. Well, there I've done it. I've tried to go through, there's a lot of equations in this section. They're all basically algebraic reshufflings of the other ones. So perhaps the most important thing from this section is the introduction of Boltzmann, the Boltzmann constant. That's something that you'll want to hang on to for later times. So number of formulas in this section. In a lot of times when we're doing chemistry or physics, we kind of make our base camp in one or two of these formulations. And then unless you have a real detailed memory, a real photographic memory, what I do is I kind of memorize some key versions and then shuffle them around when I need to in a particular problem. That way I don't have to memorize all of them. I just memorize some of the key ones and then substitute around, use common sense, and get to where I need to go for each individual problem. Well, there you have it. Man, a lot of algebra in this one. Pressure and molecular kinetic energies.